So our final speaker, Nayantara Wijayananda.
Yes, so hello everyone, it's nice to be here. Thank you for giving me 12 minutes of your time. So I'm a field epidemiologist and a part-time PhD candidate at the London School of Hygiene and Tropical Medicine. And this is part of one part of my PhD work, which is trying to understand the heterogeneity of dengue in the capital of Sri Lanka, in Colombo, and what is driving this heterogeneity. So people have already spoken about it already. Some of you already work on dengue, but if I could just highlight a few things that is important is that, so we've got 4 serotypes, and there's often co-circulation in endemic countries. There is severe disease, which is a problem with, especially with young children, and there's currently no treatment. And there's no vaccine yet that can be deployed with confidence, though it is coming. The vector is primary Aedes, primary Aedes aegypti, which is a dusk and dawn biting mosquito, which is why it creates a little bit more additional problems for us, as opposed to things like malaria, which I also work on. And it's a very efficient vector. It breeds in clean water, so even after 2 days of rain in a little bit of water, you can see breeding. So, and also control is biological and chemical, but often in some places it is mostly reactive. It is a little bit too late. Which is problematic. And we've had a lot of burden in parts of Southeast Asia and Latin America, but now it's growing, and there is increasing burden in Sub-Saharan Africa. So the rationale for my work is that these endemic countries still struggle with continuous transmission, and then these, I want to say epidemics, but these like cyclic surges that come, which puts a tremendous burden on the health system. And in Sri Lanka, we talk about 2017 because it was hard to be there, because there were so many cases Sri Lanka, dengue is one of the most important diseases before COVID hit, but still it was, the country was completely overwhelmed, and usually young kids have to be admitted to hospital, but then they were being turned away. So it was quite bad, and it's a bit frustrating that we're still sort of struggling with it. And so my work, what I wanted to do was try to help to use surveillance data and surveillance systems, which I'm really interested in, and try to find a way to use this data to help establish an early warning system, help to focus deployment of interventions, be they vaccines or something else like Wolbachia, and also reduce fatality by trying to help these systems not be overwhelmed. So, so my focus is on the capital of Sri Lanka. Oh, and also what I would like to mention is, so there's a recent paper that was published looking at the changing epidemiology of dengue. And so, it's hard to look at this, but so basically, since it was serologically first confirmed in 1962, it's become endemic, mostly in the western province there, but then it's moved across the country, and so there are peak times. So in 2010 was when the civil war was over, so like there were transport networks that opened up going to the north and the east of the country, so dengue has moved. It is still primarily, originating in Colombo, which is where the airport is, but then it moves across. So it's quite interesting for the people who study mobility. And then, as I said, there is these big surges that come every few years, which is difficult. And also, from some sentinel data, we know that there is serotype cycling. So at a particular surge, they know, okay, this was attributable to emergence of, or like replacement of one serotype. So this is Colombo, and this is what made me ask these questions, is that it is quite diverse. You have some areas which have big houses, big gardens, and it's quite flat, and then you have the areas which is getting built up, high-rise buildings, and a new port city that is being built, and how does this land use and this change in the urban environment change how dengue occurs? So firstly, yes, the built environment, and there's a rapid changes, rapid buildings are coming up. How does that change over time, change dengue incidence? Then also looking at age-specific incidence, and how does that vary spatially? Because, in relation to where schools are located. Then looking at proximity to high-risk vector breeding sites that we know that have high indices, like schools, open markets, temples, because they have a lot of containers, and construction sites, which is a big problem. Then looking at things like residential density indices that we can calculate, looking at crowding, and finally road network hubs and how the road network would potentially drive that heterogeneity. So my data is from the city of Colombo, and it's individual geolocated confirmed cases from the city for 20 years. And so basically how this happens is each time a case is, there's mandatory notification from both the public and private sector. So each time a case, each time the case is notified, there's a call that happens, and there's like a paper trail, and each case that is notified has to be followed up by a public health inspector, either in the hospital or in their home, and confirm that it is truly dengue. Now, this takes a lot of human resources, of course. So my case data is not every notified case, but those cases that were traced and sort of confirmed. And so Colombo is quite densely populated. It is a population of 753,000 in an area of 37 square kilometers. It still has the highest burden year-round, and it has 2 seasonal peaks, which is slightly different from other parts of the country. So my aim was to look at the spatio-temporal heterogeneity in cases, and look at high-risk wards specifically, because this is important for the Colombo Municipal Council, which handles both the case notification but also the vector control. And as you can see, there are 47 different wards and 6 districts, and they are administered differently, so they kind of want to know which wards are more high risk. So my initial work, and this is still work in progress, was looking at just year by year where these cases are occurring, where there is what the maps look like, basically. And part of it also was to form like a sampling for further vector studies that we wanted to do. So I did some cluster analysis using the K function and Lisa analysis to look at to confirm clustering and detect these clusters. Then some kernel density estimation, which I've shown here. And then the next bit is sort of building a spatio-temporal model of incidence using INLA. And this is just showing the same results, but showing that there is even at 1,400 meters, there is still clustering of cases. So my analysis was estimating the incidence of dengue by dividing the whole of the city into 100 by 100 meter times month grids, adjusted for spatial and temporal effects. And so this is using the R-INLA package. I won't go into more detail here, but it's basically used for latent Gaussian models. It uses a linear predictor, and the spatial process is estimated using SPDE. And it's basically you divide up your city into a mesh. And this is my model structure. So case counts in grid cells at 1 month intervals, and using spatial and temporal random effects. So my base model was just using population as a driver, and then I'm building these different types of models looking at different areas of risk. So type of residential area, fixed versus temporary, type of land use, proximity to breeding sites, and proximity to road network hubs. And my data looks like this. So some questions around like how the data was handled is what I had to go through. I'm just going to skip ahead here a little bit because of time. But so one important thing is this, because so the top part of Colombo, there's a lot of like slums and informal settlements, and the bottom is where there's more higher socioeconomic status. And so there's an assumption a little bit that there's more cases in the north, but I found it's not really the case. But it's quite interesting to look at that. And so there is a socioeconomic component. Then also looking at these known breeding sites, which are known because the ministry goes, I mean, they go and they know the indices for these. Looking at land use and trying to categorize it in this model. So basically looking at green spaces, where they are, and like distance to green spaces based on, so within an urban area, so symmetries, things like that. Oh, and then water bodies and areas of flood risk or temporary water pooling, road network. And so this is my base results. And so it looks quite similar to the simple kernel density estimation I did. Of course, there's a lot more work to be done, but this is basically the risk map using spatial-temporal model and incidence. And then going from here, unfortunately, so far I haven't found much relationship with the covariates. And I had a conversation, and maybe it's not good to have these conversations when you don't have the final results, but like they said, well, are construction sites a problem? Can we just put something? And I said, no, I can't say that. I don't have it in my model. So, and it's quite, unnerving. But this is ongoing work. I'm trying to think about, we've also validated the model, but trying to figure out, do I need to change my model? Do I need to change how I put these covariates in and how I analyze it? Each of those is a decision. And these are my main takeaways. So one was, it was access to the data, processing the data, getting it in, and then, all of that it's not simple, because all of this data comes from different agencies that don't necessarily collaborate and work together. So it was quite hard for me as one person to get it done. Geocoding, reverse geocoding, and actually just finally, because it doesn't work with Google because the addresses are not found, you just have to get one person to go and find the points and put it in a map. Computing, because each time it takes a lot of power, and also trying to understand what is most useful. Some more work is looking at crowding and trying to calculate this kind of index, and then predicting to other areas where the profile of cases doesn't look similar. That's it. So my acknowledgements and all the people that have helped me, especially with access to the data and trying to get all these data in INLA. Thank you.
Thank you.